This compass is responding to the magnetic field associated with the electron flow in the conductor beneath it. The left-hand rule for conductors shows the relationship between electron flow and magnetic field direction. With the thumb pointing in the direction of electron flow, the fingers curling around the wire indicate the direction of the magnetic field. Conversely, if the field direction is already known, the same rule can be used to determine the direction of electron flow. As we saw from Oersted's experiments, a compass needle points in the direction of the magnetic field around a current-carrying conductor. So, by curling the fingers around the conductor in the same direction as the compass needle points, the thumb gives us the direction of electron flow. When a current-carrying conductor is wrapped into a coil, the coil acts like a bar magnet with a north and south pole. The left-hand rule for coils is used to determine which end of the coil is the north pole. With the fingers curled in the direction of electron flow, the thumb points towards the north end of the coil. Since the field around the coil is similar to the field around a bar magnet, can the coil also be used to pick up iron objects? Though the coil is a magnet, it's too weak to pick up much of anything. However, if an iron core is inserted into the coil, the magnetic field strength increases dramatically, and the coil-core combination becomes an electromagnet. This powerful electromagnet can be used to pick up a wide assortment of things. When the current flowing through the coil is turned off, the field collapses and the iron core is no longer magnetic. But just what is it about the iron core that enables it to become magnetized and demagnetized almost instantly? Why is it almost impossible to magnetize copper? And why is it that metals like steel, once magnetized, retain their magnetism long after the current is shut off? For the answers, we'll need to look closely at a typical atom. Nearly all of an atom consists of empty space. Its mass is concentrated in a small, positively charged nucleus. Revolving around the nucleus are tiny, negatively charged particles called electrons. In order to follow their movement, we'll represent the paths of the electrons with circular orbits. The motion of an electron around the nucleus is much like the motion of an electron through a single loop of wire in a coil. As well as determining the north and south poles of a coil, the left-hand rule for coils can also be used to show the location of poles for the electron orbits. Each electron orbit produces a magnetic field with a north and south pole. However, the motion of all the electrons is so random that the magnetic fields tend to cancel each other out. Just so you don't think this is too simple, in addition to moving about the nucleus, each electron also spins on its axis, producing yet another magnetic field. Once again, the left-hand rule for coils can be applied to show the direction of the electron's magnetic field. Two directions of spin are possible. resulting in two different field orientations. Usually, the magnetic fields produced by these spinning electrons cancel each other out, in much the same way as the fields of the electron orbits are canceled. So the net result is that most atoms do not possess an overall magnetic field. Materials consisting of these atoms are not attracted to magnets. An important exception is iron. An iron atom has 4 more electrons spinning in one direction than in the other. As a result, their fields are not canceled or balanced. So the iron atom is left with a resultant magnetic field. Of the common elements, only 2 others, nickel and cobalt, have atoms which are tiny magnets. These atoms are said to be ferromagnetic and are referred to as magnetic dipoles, meaning 2 poles. They can be thought of as tiny compass needles pointing north. In ferromagnetic metals, these tiny dipoles interact with each other, causing large clusters of them to align themselves in the same direction. A cluster of dipoles, which all point the same way, is called a domain. Normally, domains are about 1 millimeter wide and contain millions of atoms, with each domain pointing in a different direction. But when the bar is exposed to a magnetic field, the domains which are pointing in the same direction as the field grow and take over the other domains. The core now possesses a field which is considerably stronger than the original field of the coil. When the electron flow stops, the dipoles go out of alignment and gradually form random domains again. However, with steel, the results are different. The carbon atoms added to the iron to make steel greatly hinder the iron atoms from returning to random positions when the current is shut off. As a result, the steel bar remains magnetized. Even if the bar is broken, the alignment of the domains still remains the same in each half. And so each piece becomes a magnet with 2 poles. If a magnet is struck repeatedly, the domains may gradually break free of their alignment. Heating a magnet to high temperature also causes the atoms to shift out of alignment, turning the magnet into an ordinary steel bar. As the metal cools, the atoms form a haphazard array of domains. However, if the hot steel bar had been placed in a powerful magnetic field and allowed to cool, the domains would have reformed into a strong, uniform alignment in the direction of the magnetic field. Now, when the current is shut off, the domains remain aligned, and the steel bar becomes a permanent magnet again. But what will happen if we place a current-carrying conductor into a magnetic field? The answer lies in the motor principle.